All right, so the next topic that we want to look at is jumping knowledge connection. So it has some ideas similar to skip connection. So the idea here is that we want, again, to basically deal with the over smoothing and the fact that our information are being washed out after a few iterations of message passing, right? So in one iteration of message passing, let me just bring this. Okay. So in our neural network, what happens is that we have essentially an input embedding, which we can just consider this as the embedding on iteration 0. And we pass that through our neural message passing. We get basically the embeddings at iteration 1 and so on and so forth, right? So the idea is that our last embedding, let's say that this is 2 layers. So our embedding HI2 is going to be the input to our loss function. So we're considering this to be the final node embeddings that we have constructed. So now, in order to basically prevent this information of basically the local information of the nodes that are being washed out after a few iterations, and we turn into a basically every node essentially is just containing, every node embedding is containing a global set of information, because every node is kind of getting information from everywhere in the graph. So it has lost its sense of its local neighborhood. So in order to prevent that, we can use basically jumping knowledge layer. So the idea here is that we basically, it's basically similar kind of to the previous idea, but this time we're taking all the information that we have in the first iteration. We're taking all the information that we have on the second iteration and also the last iteration, right? We put all of them together and we basically pass it to a last layer function. So that way, this function kind of as input has different basically sets of senses of the local neighborhood. So this only has information about the node itself. This guy has some information about some local neighborhood. And this guy basically after a few iteration, it has more of a global sense of the basically information around each node. So we're kind of gathering all the informations from different layers of neural message passing and passing them to a function, which can be any function that you're defining. So it should be differentiable and it should be something that is basically beneficial to our problem. Okay, so we have now basically said that we want to use all the embeddings at different layers 0 to k in order to construct our final node embedding. And to do that, we use this approach called jumping knowledge. For doing that, what we do is to just concatenate all the information, all the embeddings that we have throughout basically the network, and we pass them to a new basically function, which is basically can be anything as long as it is differentiable. Because in order to be able to train our graph neural network, you need to have a basically model which is end-to-end differentiable. So, all right. So far we have been concerned with problems that extract node features. So, and these are, for instance, basically of interest for node classification problems, but in many basic array. And So we have basically, after a couple iterations of neural message passing, we select the embedding of each node, final embedding, or after using a skip connection or basically the two functions that we introduced. At the end of the day, the embeddings that we find are node level embeddings, but in many problems, we are dealing with graph level tasks. So for instance, we have a regression problem on molecular graphs where we want to find, basically we want to predict what is the, for instance, value of some chemical property for the molecule given its graph, basically representation. Another problem that we deal with is graph classification. For instance, we have a set of graph molecules and we want to predict if they are toxic or not, if they are soluble in water or not. So in this type of problems, we need to have an embedding that is representing the whole graph as opposed to one node in the graph. In order to satisfy that, we need to basically take an approach. In general, we call them graph pooling approaches. There are two ways to perform graph pooling that we're going to discuss today. And this graph pooling basically takes ZIs, basically the node embeddings for all the nodes in the graph as input, and turns them into some, at the end of the day, as the output, it turns them into the graph level embeddings, right? So there are two approaches that we're going to discuss today. One approach is called multi-set pooling. The other approach is called graph coarsening. So in graph pooling, we define a function, FP. This function gathers all the node embeddings at the last layer and turns them into some, basically, some graph level embedding. So let's say that this is our two layers of our, this is essentially the whole of our graph neural network, which consists of two layers of neural message passing. And at the end of the day, for each node, we have embedding HI, K, which K represents last layer. The total number of the layers is equal to 2 here. Now, this pooling, multi-set pooling, essentially takes all the node embeddings and turns them into a single vector, which represents our graph. Now, if you think about this, in each layer of neural message passing, what we were doing was to gather information from different nodes, right? And we wanted to turn them into some message vector, right? So if you think about it, the idea with multi-set pooling is the same. You want to take information that are basically sitting on different nodes in the graph, and you want to gather this multi-set and you want to turn them into a single vector. This time, it's not a message, it is a vector representing the whole graph. So in essence, in principle, you can use any function that we have used for constructing our basically aggregation set in order to define this multi-set pooling. For instance, one example can be by basically averaging over all the node embeddings, right? So in this equation, we have ZG, which is our graph embedding, and we first sum over all ZIs in the graph, and then we are normalizing them using some normalizing function. This can be, for instance, just the total number of the nodes we have in the graph or any other function basically that user defines. So there is one issue with multi-set pooling. So we said that multi-set pooling is looking at the embeddings, basically at the graph as a multi-set of all the node embeddings. So what happens is that it doesn't really consider how that graph looks like. It doesn't consider if it is fully connected graph, if it's just a path or whatever. So now the problem is that you're kind of losing the information. And we don't want that. We want usually to use all the information that we have. So we want to use some model, some method that incorporates the structure of the graph into our graph level representation. And that can be done using an approach called graph coarsening. So the idea with graph coarsening is that at the multiple layers of graph neural networks, in each layer, we turn our graph into a coarser version of that graph, and then we continue that until we are left with a single node. And then the idea is that the representation for that single node will represent our graph embedding. So the idea comes from using convolutional neural networks. If you may have seen this, that in convolutional neural networks, we have an input and we have some basically sliding window of filter that we have. And we slide this over the graph, over the grid, and construct a basically new grid by aggregating information under each basically window, right? So I continue this, I move this around, and I construct a new node of this output graph. Now, if you think about this, this is just a coarsened version of our original graph. So we can, in the next iteration, we can continue this with a different size window, and we turn that into another basically coarsened version of our input, and so on and so forth, until we have basically feature representations of desired size and desired quality. So we can take this idea and we can use that in graph neural networks as well. So let's say that we have some coarsening approach. We are given some coarsening approach, and we are given this graph, right? So using this graph, let's say that using this coarsening approach, let's say that I want to turn this graph into a coarser version of this. So I take these two nodes, I combine them into a single cluster, and then in the coarsened version, I'm representing this cluster using a super node, right? So here, roughly speaking, I have combined these two, these other two into this node, these two into this node, and these two are single basically nodes here, right? So using this coarsening approach, using this clustering approach, I have basically, we could yield a coarsened version of this graph. And I can continue this for another step. I, for instance, take these two nodes, now combine them into one, these two into one, and I basically get this kind of triangle, which is representing our original graph after two coarsening iterations. And we can, every graph that we have, we can define some clustering approach. It takes nodes, it basically returns you a coarsened version of that graph. And what happens at the end of the day, after some iterations, you can basically be left with a single node and use the information on that node as representation for the whole graph. So now let's say that without being concerned about the actual approach that we're taking for clustering here, let's assume that we are given some coarsening function. We call that FC. And what this coarsening function does is that it takes graph G, it takes all the embeddings, all the nodes of this basically input graph G, which we're assuming are D dimension. So it's going to be a matrix of size V times D. So we are getting the graph itself, the basically structure of the graph and the embeddings that it has. and we're turning that into some assignment function. And this assignment function is a V by C matrix, where V is the total number of the nodes that we have, and C is the number of clusters that we have. So each row in this is showing how basically likely is for this node VI to belong to category C, for instance, to any of these categories, which we have C of them. So now when we coarsen a graph using this function, what happens is that we're basically mapping this graph along with its embedding into this assignment matrix, right? And we can look at it this way. For instance, in the previous graph that we have, had we had 5 clusters, we were trying to assign different nodes into one of these 5 clusters. So since we had 8 nodes, we would have had an 8 by 5 essentially assignment matrix representing this clustering from this step to the other step, right? So now let's say that we are given this assignment matrix. Using this, we can basically use this relation and basically compute the adjacency matrix that corresponds to the coarsened graph, right? Where now A prime is the new adjacency matrix. It has basically C clusters, so it has C nodes now, the coarsened graph. So our adjacency matrix is gonna be a C by C matrix. Now the C by C matrix, if you think about it, we had this basically assignment matrix multiplied to it, and our original graph adjacency was essentially a binary matrix, right? It has only zeros and ones on it, but it is no guarantees that the new output, the new basically coarsened matrix is binary as well. So it has real values, but these real values represent how basically the strength of the relation between 2 clusters. So some values are going to be 0. The other values are going to be just some real number. And these real numbers are going to represent how strong is the basically connection between 2 different clusters. So again, similar to the way we coarsened the graph, we can also coarsen the feature representations that are residing on the graph. Right? So let's say that we have H as the embedding matrix for our input graph, which has dimensions V times D. Now, using this relation, we can coarsen the representations that we have into representations for the updated matrix. And that's going to have a dimension of C times D, C being the total number of the clusters, now representing the nodes on the coarsened graph, and D, the representation of the embeddings. So now what happens is that using this relation, what we have done is kind of aggregate information that we had on the nodes of each cluster into one vector, right? So, which is good. So it means that each row on this basically representation is gonna represent one of those clusters that we constructed when we were coarsening. So with that said, what we can do is now we have a new graph. We can apply a new layer of graph neural networks on this in order to further extract information on basically this graph, right? So let's say that I have some original graph that I basically apply some neural message passing layer on this. And then after that, I have some updated embeddings. I'm showing that with H1 for node I. And then I apply some graph coarsening step, which takes this embeddings as input and the graph as input, and it returns some coarsened graph with some coarsened feature representations, right? So like any other graph, we can pass this through basically another aggregate and update iterations in order to get some new feature representations. Now, if you continue this until you have a single node, that will essentially represent feature representation for the whole graph. And that's the idea with graph coarsening. So now we can use many approaches for spectral, for basically clustering nodes of the graph into basically some coarsened graph. Now, for instance, we looked at spectral clustering approaches earlier in this semester. We can use those, for instance, but the problem with those is that they are not differentiable. So if we want to train our graph, our basically graph neural network model, we need to have layers that are differentiable in order to use backpropagation to update parameters of this model. So one constraint for selecting this clustering approach is that it should be differentiable. So basically, you can define any approach that is differentiable. For instance, it can be just a, it can be, so if it's deterministic, I'm not, off the top of my head, I can't really think about any deterministic approach that is differentiable, but it's probably, there is, you know, just, there is probably just dividing this by some approach. Anyways, so the idea is that if it's not differentiable, you can't use it. That's the only constraint that you have. So far we talked about clustering different nodes into essentially one super node and coarsen the graph. Another approach for coarsening the graph is that we kind of go through the graph and we eliminate the nodes that are not basically that can be eliminated, right? That we have different criteria to do that. Maybe they are not that important of the nodes or any other approaches. We are not going to cover that here, but just mentioning that that's another approach that you might encounter in literature.